It was not swampland.
All right, so thank you very much for having me here. It's great to see many of you back in 3 dimensions and not just holographically. So in this talk, I'd like to tell you about Euclidean wormholes and the swampland. And I put a question mark in the title, not because of Hinchcliffe's rule. Rather, it's an honest question that I'd like to know the answer to. And so let me start with some motivation. So Euclidean gravity has been useful in studying tunneling as well as thermodynamical aspects of gravitational systems. For example, to compute the thermodynamics of a black hole, our starting point is usually the Euclidean action. Now, despite its successes, it's fair to say that Euclidean gravity has generated more puzzles than its non-gravitational counterparts. So in quantum field theory, wave rotation transforms an oscillatory Lorentzian path integral into a convergent integral in Euclidean signature. Take a scalar field theory as an example. After wave rotation, the Euclidean action is nicely bounded from below if the potential is. As a result, the Euclidean path integral is convergent, with its dominant contributions coming from local minima of the action that we call saddles. Unfortunately, gravity does not play so nicely. So, in contrast, the Euclidean action for gravity is unbounded from below. We can see that by rescaling the metric with the conformal factor. So after this rescaling, you see that you could get Euclidean action as negative as you want by choosing a rapidly varying conformal factor. Now, this is the so-called conformal factor problem and can be solved by the Gibbons-Hawking-Perry prescription. So after wave rotation to Euclidean space, you could further rotate your path integral contour such that the conformal factor takes imaginary values. So if you do that, the Euclidean action is still bounded from below. The Euclidean action is still bounded from below. Now, this prescription, while does the job, may seem rather awkward to you. If you accept complex metrics, you may as well not wave rotate in the first place. So one may wonder whether one can work directly with the Lorentzian path integral and whether complex metrics contribute to the path integral. Already, there is evidence that complex metrics are required to make sense of pure 3-dimensional gravity. And recently, a set of allowability criteria for complex metrics was proposed by Konsevich and Siegel. So a complex metric is said to be allowable if any p-form gauge theories coupled to the complex metric still gives convergent path integral. So that's what they mean by allowability criteria. It sort of looks like the opposite of the swampland. Instead of asking what quantum field theory can be coupled to gravity, here we are asking what metrics can couple to gauge theories. Now, it remains to be seen whether this allowability criteria are necessary or sufficient for coupling any matter theory consistently to gravity. So with this motivation, together with 2 students, we recently looked at Lorentzian path integral. We try to find a way to evaluate this Lorentzian path integral using something called Picard-Lefschetz theory. And I will briefly review what it is as we go along. And so as you will see in our approach, Lorentzian, Euclidean, or complex set of points are treated in a very democratic way. Now, another peculiarity with Euclidean gravity is the existence of wormhole solutions, most famously the Giddings-Strominger wormhole. Now, these wormhole solutions lead to a lot of puzzles. One of them is the breakdown of locality, because now you could write down operators that involve 2 different space-time points. Now, Sidney Coleman taught us a long time ago how to bring this wormhole action back into a local form by introducing a set of so-called alpha parameters. However, in this picture, the coupling constants in nature depends on the alpha vacuum, and one is only led to make statistical predictions rather than precise predictions.
How are the alphas determined?
They are not determined. So these are distributions of alphas. Right? So you could ask, what's the probability of finding a certain coupling, like the cosmological constant and so on. If the probability is peak at 0, then this is how Coleman would say that we are living in the universe with 0 cosmological constant because the probability is high. We are not fixing the constants in nature in any ways. Now, this Euclidean wormholes are even more puzzling if they're embeddable into AES compactification of string theory, because they jeopardize factorization in AES CFT. So if you compute correlation functions of 2 different boundary CFTs, you would expect that the correlation functions should factorize, but the wormhole solutions tells you that they may not. There are many proposals of explaining this puzzle of factorization. One of them is that perhaps the solutions, these Euclidean solutions, wormhole solutions, like the Giddings-Strominger wormhole solutions, are not stable. If they are perturbatively unstable, that may explain away the puzzle with factorization. However, previous analysis either have not taken into account gauge invariance, or the correct boundary conditions have not been imposed, leading to rather contradictory claims. And this issue of wormhole stability for axionic Euclidean wormhole has not been settled in the past 25 years. So we find that when all these issues are dealt with properly, when gauge issues and boundary conditions are dealt with properly, the Giddings-Strominger wormhole is actually perturbatively stable. We don't find any perturbative instability. So that's what I'm going to tell you in the second part.
Sounds like a good news, but it's bad news.
It's good news and bad news. It's good news because they at least should contribute to the path integral. And the bad news is they lead to all kinds of puzzles like non-locality and factorization and other type of factorization. Okay, so in fact, that's a good place to repeat some of the things that we said. The existence and stability of wormholes is also relevant for the Swarmland program. So wormholes, among other things, break global symmetries, which have long been conjectured to be inexact in quantum gravity. So at least we know that there is one source of such breaking if the wormholes exist. So it seems like we would like that to be there and be stable. They also play a key role in formulating the axion version of the weak gravity conjecture. This is the form of the weak gravity conjecture that could constrain some models of inflation that gives detectable wave signal. The weak gravity conjecture was originally formulated in terms of one-form gauge fields. So the weak gravity conjecture for one-form gauge fields requires an extremal charged black hole to be able to decay. Without a clear notion of extremality for minus one form symmetries, wormholes have been used to set the weak gravity bound. And the weak gravity conjecture for axions take the following form. Instead of the charge to mass ratio of particles, it requires the product of the axion decay constant and the instanton action to be bounded by the Planck scale. So intuitively, it offers an explanation why it is so hard to find super Planckian decay constant in control constructions of string theory, because the moment when you get a decay constant that is super Planckian, the instanton action becomes small, and so you lose control of all the possible higher order corrections. So it would be good if there are wormholes in order to set this order one factor in the weak gravity bound for minus one form symmetry in the same way that extremal black holes sets the order one factor in the ordinary weak gravity conjecture. On the other hand, the alpha parameter interpretations of wormholes, like what was described a slide ago, leads to a -1 form global symmetries. It is global symmetry, so it should also be forbidden.
-1 form.
-1 form means that it's an instanton. So a particle is a zero form, it couples to a 1 form gauge field. So we call this a zero form symmetry. The ordinary gauge field is a zero form symmetry. So whereas for the case of an instanton, it couples to an axion. So the axion is the analog of the gauge field. And the naming of the symmetry is such that we name the object that coupled to the gauge field. So that's why we call it the -1 form symmetry. And the -1 form symmetry always comes along with an axion, which is the zero form that coupled to that object. And that's a very good question, because unlike black holes, we don't talk about extremal instantons in the same way. Right? So we don't talk about decay of an instanton. So it's less clear how to put this bound for anything that coupled to the axions. So that's why this order 1 factor has not been explicitly fixed. We know that smaller than the Planck scale, but the precise factor would rely on having some reference. And in the case of black holes and weak gravity conjecture, we know how to fix that order 1 factor. We just take the charge to mass ratio of an extremal black hole. For instanton and axion, there is no such extremality bound. And so without anything better, we can take a very large wormhole as a reference. That's what has been done.
Axion always has derivative couplings though, right?
It does, yeah.
So how does it couple then as a gauge field, quote unquote? I mean, you want us to think of it like in analogy with the gauge field coupled to an instanton. So sorry, to a charge field, charge particle. So how does it minimally, is there a notion of minimal coupling? How does it couple?
So in fact, these are all very good questions. And the only way we know how to do that, as far as I know, is in cases where we know how to map the instanton and the axion to ordinary gauge field and particles. We know how to fix that, right? So in all these papers, you are either using duality or using dimensional reduction. So you can dimensionally reduce the ordinary gauge field to get a 1 form gauge field to a 0 form gauge field. Since you know the weak gravity statement in high dimensions, you can infer what that means for the axion and instanton. But other than that, I don't know of a good unambiguous way.
That helps. Okay, thank you.
Okay, so now one can also check that the higher derivative corrections lower the Euclidean action for a wormhole, just as what the weak gravity conjecture seems to suggest. So all in all, I hope at the point that the situation is rather confusing. We don't know which way, we don't know whether this suggests that wormholes should exist or not, at least as a stable settle point of a path integral. And so it would be important to find out whether Euclidean wormholes are in the swampland. And if not, how to interpret them. Yes.
So when you say derivative corrections lower the wormhole action, they both modify the solution and then you plug back the solution to the full angle.
Yeah.
The whole thing is slow.
Yeah. So you could ask if I have a wormhole with a given charge. So these are all charged wormholes. So they are carrying axion charge. So you could have a very big wormhole with some axion charge, and it could fragment into smaller ones. So the question of interest for the weak gravity conjecture is whether this fragmentation is allowed, just like large black hole can decay to smaller ones. So it amounts to comparing the action of all the small wormholes with together the same charge as the big wormhole to begin with. And we can check that this seems to be the case. Large wormhole with some charge has a bigger action than the sum of small wormholes with the same charge. But these are all suggestive evidence. I don't think I could say more and say that this is a proof of the weak gravity conjecture in any ways. Okay, so this is the plan for the rest of my talk. I will show you how to evaluate Lorentzian path integrals using Picard-Lefschetz theory. And so maybe not all of you are familiar with what Picard-Lefschetz theory is. I would briefly review that. And so this approach which was previously used to study quantum cosmology, would treat Lorentzian, Euclidean, and complex saddle points in a democratic way. And in this approach, the Lorentzian saddle points for the axion gravity system that we study describes Freeman-Robertson-Walker universes, whereas the Euclidean wormholes corresponds to the Giddings-Strominger wormhole. And you will see that which type of saddle points appear depends on the initial and final configuration of the transition amplitude that we compute using the pattern network. Now we then turn to wormhole stability. We analyze quadratic fluctuations around the Giddings-Strominger wormhole solutions. And taking into account gauge invariance and proper boundary conditions, we find that the perturbations do not lower the action. The homogeneous modes turn out is a pure gauge mode. It's not a physical degrees of freedom. There's no conformal factor problem. Whereas the inhomogeneous modes that could be localized at the neck throat, they increase the Euclidean action. So in other words, our conclusion is that an axionic Euclidean wormhole is perturbatively stable, based on what we said. Okay, so since we will be talking quite a bit about the Giddings-Strominger wormhole solution, let me just remind you what it is. Giddings-Strominger wormhole arises as a solution to the Euclidean equation of motion for axion gravity. So in this case, I'm interested in four-dimensional axion gravity. Take axion coupled to gravity, go to Euclidean signature, and write down the equation of motion. And then you will find that there's a solution that is given by the metric and the three-form shown in the slide. The wormhole connects or interpolates between two asymptotically flat regions. And the size of the wormhole is set by the three-form flux, which is quantized. And this three-form flux has the interpretation as the axion charge in the axion picture. So there are two different ways to describe this axion gravity system. Either you describe it as axion coupled to a pseudoscalar, to an axion gravity system, or you could describe it in terms of a gravity coupled to a three-form. This is the dual form relation. And so in the three-form picture, the metric and the three-form naturally satisfies Dirichlet boundary conditions. So if you have perturbations of that solution, the perturbations should go away as you are far away from the neck of the wormhole. So you're fixing the metric and the three-form at the boundary. Whereas there is no boundary conditions for the Lagrange multiplier theta, which has been introduced to impose the constraint that H is closed. Okay. So in the three-form picture, theta appears as a Lagrange multiplier, and you can integrate out this Lagrange multiplier and get an action for the two-form gauge field. This is one way to describe this wormhole axion gravity system in terms of a two-form gauge field coupled to gravity. On the other hand, you could also try to integrate out the three-form by completing the square. And there you find that in the axion picture, when you integrate out the three-form, theta is a dynamical field. Moreover, there is a boundary term that you generate. Okay. So even though this boundary term does not affect the equation of motion, it can be viewed as imposing Neumann boundary conditions for the axions. So if you were to fix the three-form flux, in the dual formulations, you are fixing the axion charge, which is basically fixing the derivative of the axion field. So the axion satisfies Neumann boundary conditions, whereas the three-form satisfies Dirichlet boundary conditions. Now you are free to choose either one of this description as you want. In the Euclidean path integral approach, the Giddings-Strominger wormhole is more apparent in the axion picture because of the wrong sign kinetic term. So if you go to Euclidean space, if you write down the Euclidean action for axion coupled to gravity, the axion kinetic term appears to have the wrong sign.
So when you say axion, you should think of the scalar field description. Okay. Okay. Okay.
But as you will see, in our Lorentzian approach, wormhole solutions can be found equally easily in both pictures. You are free to choose. You can go to the zero form picture or the three form picture. You will be able to see how the wormholes appearing in the path integral.
Are these two theories equivalent at the quantum level?
They should be equivalent at the quantum level.
Provided that I keep track of the total derivative term, right?
Yes.
That is important. But because in the past there were papers written, I think Mike had a paper with Van Nieuwenhuizen, in which they argued that there are differences in, if the space-time had different topology. So in other words, the way I interpreted their results was they were not quantum equivalent, I thought. So let me rephrase my question slightly different way. If I quantize these two theories, the way you described them, bottom line, in two space-times that are different topology, are they equivalent? Will they give equivalent physics?
So when you compare, you should compare two with the same topology.
No, I fix a space-time topology, but I use either theory 1 or theory 2.
You can use theory 1 or theory 2, but
I'll get the same answer.
you should get the same answer if you keep track of the boundary terms. For instance, if you were to drop these boundary terms, you would have come to a different conclusion. That's essentially a lot of the papers that look at stability of the wormhole solutions. We're looking at it from the axion picture instead of the three-form picture. And then well, this is a boundary term, so it doesn't affect any of the equation of motion, anything. But it's telling you that the boundary conditions for this axion field theta is Neumann rather than Dirichlet.
But in literature, there must be quite a misunderstanding then, because there are many papers in which they go on about quantum inequivalence of, dual formulations. Townsend had papers on this and so on. But anyway, later we can discuss. Okay.
Discuss it further.
Partition functions differ by topologically invariant.
But does that mean they are quantum equivalent or inequivalent? Those two models, I mean.
That's inequivalent.
Right, that's what I thought until today. But now I'm told that they are equivalent.
Well, also, we are not probing too deeply into quantum aspects of it. We are looking at perturbative instability. We are taking a classical solutions and do quadratic fluctuations around it. Maybe for questions like that, you don't see the equivalent. We do find a way to see how summing over topologies can affect the Lorentzian path integral using this Picard-Lefschetz approach, but we don't claim to understand the full picture.
Oh, so what Mike is saying is that there's some overall factor that's different, but it doesn't matter for your purposes.
At least I think what I would be studying would be a classical perturbative instability. So you could always ask, given a classical axion gravity system or three-form gravity system, suppose you have a saddle point, you could ask whether this is really a minimum of the action or not by checking whether the quadratic fluctuations lower the action. So here you don't see much of quantum in it, but there have been a lot of confusing aspects of this problem. I hope to explain to you sometime in this talk.
Okay.
So in analyzing the perturbations around the axionic wormhole, the boundary conditions in the three-form pictures are more straightforward, and this is because normalizable perturbations of the three-form has finite energy. So normalizable means that when you calculate the norm of the fluctuations, it's bounded. And for such perturbations, it also has finite energy because the energy goes to h squared. Whereas the corresponding finite energy perturbations of the axions are not necessarily normalizable. This can be seen from the axion shift symmetry. If you give the axion a constant shift, you don't add any energy. The energy is measured by the derivative of the axion, but it gives you a divergent norm. Okay, so this would not have been a problem if you don't consider gauge invariant perturbations around the gravitational solution, but you do when you study stability. So the metric perturbations naturally vanish at the boundaries, naturally vanish at regions far away from the wormholes. So are the free-form perturbations. So when you combine the metric perturbations with the free-form perturbation in the gauge invariant manner, you can implement that boundary conditions very easily as Dirichlet boundary conditions. Whereas in the axion picture, the axion perturbations satisfy Neumann boundary conditions, whereas the metric perturbations satisfy Dirichlet. So the gauge invariant combination mixes different types of boundary conditions. And this is the source of some of the mistakes that have been made in the literature in the past. Okay, so let me start with Picard-Lefschetz theory. Now, the price to pay in working with Lorentzian path integral is that they are oscillatory. They are not naturally converging object. Now, as the gravitational path integral that we study, oftentimes reduced to ordinary integrals, we will see why that's the case. Let us start with Picard-Lefschetz for ordinary integral as the warm-up to see how Picard-Lefschetz theory allows us to evaluate oscillatory integrals. Okay, so the idea is to promote the exponent or the action to a holomorphic function on the complex plane. So using analyticity, you can deform the contour to make the integral convergent and non-oscillatory. Now, evaluating an oscillatory integral like that therefore amounts to finding the saddle points and the steepest ascent and descent contours through them. And we will call the steepest descent contours Lefschetz thimbles. Now, you could parameterize the steepest descent curve away from the saddle point by this parameter lambda. And so this Lefschetz thimbles, the one that goes along the steepest descent, follows this downward flow. Now you can use this flow equation to show that the real part of the action, also known as the Morse function, decreases along the flow. That's what we mean by steepest descent curve. And moreover, the imaginary part of the action stays constant along the flow. So if you manage to find this Lefschetz thimbles, integration along that thimbles would give you a convergent and non-oscillatory integral. Okay, so now given an oscillatory integral, you can rewrite it as a sum over integrals along thimbles, different thimbles, known as Lefschetz decompositions. So you are doing many saddle points approximations. You are approximating the full integral that you want to evaluate in terms of integrals over many of this steepest descent curve. Now, this integer coefficients, which takes the value 0 plus or minus 1, picks out exactly which thimbles contributes to the integral.
How do I know there are finitely many such objects?
You have to look. If there are no finite number of them, this method does not work. So in the cases that we study, we have 4 saddle points, and so each saddle point has.
You actually determine them. You don't assume anything. You just find them, and there are finitely many.
Right. Yes.
Is this an approximation to your original integral, or is it just giving?
Yeah.
It's an approximation.
It's an approximation. So it's a saddle point approximation. If it is not a saddle, we will see some examples where the saddle point approximation works very well. And so you basically approximate the integral by a bunch of Gaussians with possibly a different phase coming from each saddle point. So things start to fail when the saddle points collide. So if the saddle points are separate from one another, this approximation works very well. You see in a very simple one-dimensional integral that when the saddle points collide with each other, that's the region where the approximation breaks down. Okay, so now this integer coefficients can be determined by the intersection numbers of your integration domain with all this steepest ascent contour. And since this intersection number is a topological quantities, they do not change as you deform the contour back into the original wheel domain. So in other words, you turn the problem into a problem in terms of the topology, you can calculate the number of, you can calculate the intersection numbers, and then you're done. You can do your Gaussian integral and find the answer. Now there's a potential complication due to this. The steepest descent path from one saddle point run into another saddle point, then this decomposition is ambiguously defined. However, in such case, you can oftentimes resolve the ambiguity by giving H bar a slight small imaginary part to make the symbols unambiguously defined, and we see some examples of that. Okay, so as an illustrative example, let's consider the Airy function. The Airy function is a solution of this differential equation. Its integral representation is highly oscillatory. So if you were to plot the real and the imaginary part of this integrand, it's oscillatory like that. The saddle point is given by equation. And there are two saddle points. If x is negative, the saddle points are real. If x is positive, the saddle points are purely imaginary. Okay, so all right, so let's consider the negative x case to illustrate how Picard-Lefschetz theory pick out contour deformation and select saddle points. So in the case when x is negative, there are two real saddle points on the real axis here. Now the color coding in this picture is such that the real part of the action becomes more and more negative in the greener region, and is more and more positive in the redder region. So suppose this is your integration, this is your Airy function to begin with. The contour is the dotted blue line. You could deform your integration contour, avoiding the red region where the integral is divergent. So we are instructed to deform the contour in such a way to avoid a divergent region. So we could deform it, and using analyticity, it crosses two of the saddle points. And since the integration contributions is very small in the green region, this is when the exponent becomes very negative. We could hop over from one saddle point to the other. And so this would be our deformed contour. And the saddle point approximation, as correctly pointed out, we are only doing a saddle point approximation. So we are treating this integral as Gaussian around the saddle points with possibly a different phase around each saddle. So this would be the answer if you use Picard-Lefschetz to evaluate the Airy function. So if you were to look at the phase, you find that the phase around each saddle point is constant. And it is highly oscillatory in the middle. But the contributions in the middle around around z equal to 0 gives the vanishing contributions to the integral. So you won't lose much by ignoring this part of the integral. So approximately the Airy functions by two saddle points using Gaussian approximation is a very good result. This is the case when x is negative. When x is positive, the saddle points are purely imaginary. So these are the two saddle points here. And we can deform the contour again, avoiding the red region where the integral is divergent. Unlike the negative x case, even though there are two saddle points, only one of them contributes to the integral. Now you can ask, how well is the saddle point approximation? It works very well for both both positive and negative x, unless you are very close to x equal to 0. And you know why the approximation failed, because that's when the saddle points start to collide.
Is there a parameter in the original Airy function? Can you go back to the function itself? There's no parameter that I could view as a perturbation parameter or something like that, right? I mean, if I want to know how good is your result, wouldn't it be useful to have some parameter which would I could compare the result with? I mean,
well, we know the answer. So in this case, is we know exactly what's the correct answer without any approximation. So we are comparing the actual answer with the approximate settle point result.
suppose I don't know the exact answer. How do I know how good is my answer?
You do perturbation theory around the Gaussian saddle.
Yeah, but don't I need some perturbation parameter?
Well, that's what the asymptotic expansion is. So the term that Gary's evaluating is the leading term in an asymptotic series. And you just do perturbation. Did you just develop the expansion and powers of, I believe, X to some power around the Gaussian saddle.
So X is the culprit then maybe. Okay, all right.
You can rescale the variable to make it.
So lowest order is a Gaussian, higher order would have some.
Do you rescale X or Z?
Okay, so
Z.
that was ordinary integral, and now we could move on and try to see how we could evaluate Lorentzian path integral, gravitational path integral using Picard-Lefschetz methods. Agreed. We consider transition amplitudes between two boundaries of S3 topology. So that's the path integral I wanted to evaluate. And I'm considering a homogeneous isotropic ansatz. So the Lorentzian path integral is evaluated on this homogeneous isotropic ansatz for the metric and for the three form. So it's homogeneous isotropic because I don't have any spatial dependence, only time dependence. And you could equivalently evaluate this transition amplitude in terms of the axion picture. If you don't want to work with the three form, you can do it for the axion. And indeed, we did that both. Okay. Now, the transition amplitude vanishes unless the fluxes, the three form fluxes N0 and N1 at the initial and final configurations are the same. And we would denote that common flux by N. Right? This is because of the constraint in the three form picture. The fact that the transition amplitude vanishes unless this condition is satisfied follows from the constraints on the three form. That d of h is equal to 0, or alternatively in the axion picture, this follows from the shift symmetry. And the shift symmetry requires that the flux N0 and N1 to be the same, or this transition amplitude to be non-zero. Now, so the strategy that we would use is to first evaluate the path integral for Q, or any boundary conditions Q0 and Q1. And then we'll use Picard-Lefschetz theory to evaluate the remaining one-dimensional integral over this Lefschetz function N. Okay, now there are two solutions for Q for the, that satisfies the boundary conditions. That is equal to Q0 at t equals to 0 and Q1 equals at t equals to 1. And both solutions are displayed here. One of these solutions is nowhere 0 in the interval parameterized by t, whereas the other solution always passes through 0. So only one of them is a valid saddle point, because otherwise the metric collapses at this saddle point. And so evaluating Q, the Q path integral, taking only the valid saddle point, we are left with an oscillatory integral of this remaining function N. Now compared with the Airy function, this integral is a little bit more involved. It has branch cuts. Nonetheless, we can still use Picard-Lefschetz theory to evaluate this path integral. We have to be a bit more careful in avoiding the branch cut at the branch points. Okay, so this is the transition amplitude as an integral over N. As you can see, just like the Airy function, is highly oscillatory. And turns out for this problem, there are 4 saddle points for N. And the location of the saddle point and how we form the contour depends on the initial and the final configurations. And they fall into 3 cases. The first case corresponds to both Q's smaller than N. In this case, all the saddle points are on the real axis. And the steepest descent curve intersect the two positive saddle points at 45 at plus or minus 45 degrees. And the contributing saddles are the saddles in blue. They are Lorentzian, and they describe FRW universes. Now, since they are Lorentzian saddles, they contribute as phases and could lead to some interference effect. When you do this saddle point approximation, you are summing over these two saddle points that have different phases. And so this is where the interference effect occurs. And so here I have not shown you the explicit form of the functions. You can find the function in our paper. I won't show you the function here because they look rather awful. But the basic physics is very simple, that you are having interference of the two saddles, all Lorentzian saddles that describe FRW universes.
The red lines, they are the branch cuts.
Yeah, so these are the branch cuts. So we can choose our branch cut. In this case, we don't have to worry about them. So turn out in one of these cases, the descent contour intersect the branch point. So we have to do some surgery to make sure that we are not avoiding that. Okay, very good question.
In the cosmological setting, I remember that this integral over the Labs function, they discuss whether you should integrate from 0 to infinity or minus infinity to plus infinity. We have.
Yeah, so we're here integrating from 0 to infinity, right? So I don't know the reason why we would have to integrate from minus infinity to infinity.
I think the argument was the integral over the Labs function will impose the constraint, and you can only get the constraint from minus infinity to plus infinity.
So here we don't have this issue, and so the answer has n squared. So if you want, you could integrate from minus infinity to infinity, but it's twice as big. Okay, so the second case corresponds to n in between the q's. Here, all the saddle points are complex. They're not purely real or purely imaginary. And the steepest descent contour, when you deform it, avoiding the red region, would intersect only one of the four saddle points. And the interpretation of this saddle is less clear because the metric involves both real and imaginary parts. However, if you look at the transition amplitude, which you can compute using Picard-Lefschetz theory, you find that it looks like a Lorentzian evolution from Q0 to N, and then tunneling phenomenon occurs from N to Q1. And finally, case 3 corresponds to both Q's bigger than N. Here, all the saddle points are on the imaginary axis. And moreover, the steepest descent curve now intersects the branch point. And so the Lefschetz decomposition is ambiguous, and we should find a way to resolve that ambiguity. And one way to do that is to give H bar a small imaginary part. It has the effect of deforming the contour such that only one saddle point is picked out and no longer hit the branch point. And this Euclidean saddle that is picked out by Picard-Lefschetz describe a segment of the Giddings-Strominger wormhole. So you can think of the wormhole as parameterized by this metric, and it goes from Q0 to Q1. That segment is what this Lorentzian path integral pick out using Picard-Lefschetz theory. And again, you can identify the exponential suppression of this transition amplitude with the action of the Giddings-Strominger wormhole. Okay, so this picture illustrates how the transition amplitude differs for the 3 cases. On the right, we have case 1, where you have 2 Lorentzian saddles that interfere with each other. This corresponds to case 2 with a complex saddle. And this corresponds to case 3 with a Euclidean saddle. So you see that whether the saddle is Euclidean, Lorentzian, or complex can be treated in a democratic way in this Lorentzian path integral approach. And that's one of the advantages of looking at Picard-Lefschetz theory for path integrals. Okay, so I will be quick with the axion picture because many of the same features carry over to the axion case. And you can again try to use Picard-Lefschetz to evaluate some highly oscillatory integral. This time the integral is not over n, but rather over the axion theta. And you see that the location of the saddle points and the deformation of the contour falls into 3 cases, matching exactly what was found in the 3-form analysis. And evaluating on each of this saddle, give you a perfect agreement with the 3-form results. So whether you want to evaluate the transition amplitude in the 3-form picture or the axion picture, you would have gotten the same results regardless. All right, so in the remaining time, let me turn to wormhole stability. So what we have established previously was that the Giddings-Strominger wormhole homogeneous solution is a saddle point of the Lorentzian path integral. But we know if this wormhole is stable to inhomogeneous perturbations. So after all, the wormhole has a neck, and around the neck region, suppose there are perturbations, could the wormhole stabilize? Could the perturbations destabilize this wormhole? Another question you could ask is whether there's a conformal factor problem associated with the homogeneous mode. Now, whether these Euclidean wormholes are stable or not is important for resolving puzzles such as on locality and the lack of factorization. So we would like to know whether they contribute at all. If they are unstable saddle points, maybe they won't contribute to the path integral. As I mentioned, previous analysis have not taken into account both gauge invariance and the correct boundary conditions, meaning that when you perturb the solutions, you should fix the axion charge, and has led to some contradictory claims. And so for reasons that I explained before, we will analyze the perturbative stability of the Giddings-Strominger wormhole in the 3-form picture, where the boundary conditions and gauge invariance can be implemented more straightforwardly. So to determine whether the wormhole is stable or not, we carry out the following steps. So first, we parameterize the scalar perturbations around the wormhole solutions and identify the boundary conditions. Now, not all of these perturbations are physical. Some of them can be gauged away by diffeomorphism. So the physical degrees of freedom are the gauge invariant combinations of the perturbations. Then you can expand the action to quadratic order in the perturbations. Now, after integrating out the non-dynamical degrees of freedom and the unphysical gauge-dependent modes, you are left with only the physical dynamical degrees of freedom. And we want to know what this physical dynamical degrees of freedom do to the action. You could study the spectrum of these perturbations and see whether the action is lower or increased with these perturbations. If there is a mode such that the action is lower, that means that the wormhole is not really a genuine saddle point. Now, some of you who have studied gauge invariant perturbations in inflationary cosmology may recognize some of these steps. In fact, a lot of these calculations look really similar, but what is different, as you will see, is that the on-shell value of the quadratic action, and not only the spectrum of perturbations, is important for determining the stability of the wormhole. So now we will stay in Lorentzian signature for as long as possible until it's absolutely necessary to wake rotate. And the scalar perturbations can be parameterized as follows. So without this scalar perturbations, we have a homogeneous answer for the Giddings-Strominger wormhole. There are 6 scalar perturbations, 6 independent scalar perturbations you can write down. All of these perturbations vanishes as you go far away from the neck of the wormhole. And so the boundary conditions for them would be Dirichlet boundary conditions. Now, some of these perturbations are unphysical and only represents the freedom to perform diffeomorphism. So under diffeomorphism, these perturbations transform according to the Lie derivatives of the 3-form and the metric. And so we can figure out which combinations of these perturbations is gauge invariant. Now, physically meaningful statements can only be made about the gauge invariant combinations of the perturbations, not perturbations that are not standalone in a gauge invariant way. And in this problem, turns out there is only one physical gauge invariant mode. It's a combination of perturbations of the free form and perturbations of the metric. So if you go back to how I parameterize the perturbations, the gauge invariant combination involves a bit of S, which is the perturbations of the free form, and a bit of E, which is some perturbations of the metric. Okay, so now it's very straightforward to expand the action to quadratic order in perturbations. And you notice that among the 6 perturbations I have written down, not all of them are dynamical. Some of them appear in the action, but without the time derivatives. So these non-dynamical fields include B and W. So when you expand to quadratic order, you don't find B dot or W dot in the expression. This non-dynamical degrees of freedom, when integrated out, impose constraints. That's familiar in many gravitational systems. And we would like to further simplify this problem by reducing it to a one-dimensional problem. That can be done if we expand all these perturbations in terms of the angular momentum eigenstates. So remember, we are looking at transition amplitude. We're looking at something with S3 topology. We can expand in terms of eigenstates of this S3. And so the eigenvalue of S3 will be given by lambda of J. Okay, so there are infinitely many of these modes. And we could write down the quadratic action for them one by one. So we will start with the homogeneous mode, which corresponds to J equal to 0. So this has no angular dependence, if you wish. And if you look at the quadratic action, only 2 of the perturbations appear, phi naught and psi naught. The other perturbations do not appear in this order for the homogeneous perturbations. And one of them is non-dynamical. Phi naught is non-dynamical. When you integrate out that field, the effect is to impose some gauge invariant constraints. And when you put it back into this action, you find that the homogeneous modes give you an action that is a total derivative. So that means that the homogeneous mode is not a physical degree of freedom. There's no conformal factor problem. And similarly, you can show that the J equals to 1 mode is also a pure gauge. You could show that after you integrate out the non-dynamical field, you get something that is a total derivative. What is interesting are the other, in fact, infinitely many perturbations you can write down for J bigger than or equal to 2. And in the case when J is bigger than or equal to 2, there's only one gauge invariant perturbations that I call S. And this is the quadratic action after you have integrated out all the other degrees of freedom, whether they are non-dynamical or gauge-dependent modes. There's only one mode left, which is S of J. And at this stage, there is no obstacle to performing the standard wig rotation. We would now wig rotate the action to Euclidean and check whether the perturbations increase or decrease the action. The homogeneous solutions describe the Giddings-Strominger wormhole. And in this coordinates, R equals to 0 is the neck of the wormhole, whereas the 2 asymptotically flat regions corresponds to R equals to plus or minus infinity. So the wormhole is going from minus infinity to plus infinity. In the middle, when you have the neck, that's when R equal to 0. Now, this action is still not entirely nice because of this cross term. We would also like to canonically normalize the perturbations. So after you canonically normalize the perturbations, and using integration by parts to get rid of this cross term at the expense of generating some boundary term, this is what you find, the quadratic action as a quadratic action. So if you stare at this action, you may naively conclude that this action is positive definite, so you don't have to do anything. So here I have not given you the expressions for the potential U and the boundary term, but they're given in the paper. So if you just look at the first 2 terms over here, it looks like they are positive definite. So shouldn't the perturbations always increase the action? Turns out one has to be more careful. The boundary terms turn out to be key, and you have to be more careful in checking whether with the inclusion of the boundary terms, the action is lower or not. Okay, so finding the spectrum of perturbations amount to solving this Schrodinger-like problem. So you have the second derivative, some potential, and you want to find eigenvalues. Now, our physical perturbations die off at infinity. So all the metric perturbations, the free-form perturbations, should go to 0 when you are far away from the neck of the wormhole. However, because of the rescaling that we have done, the rescale perturbation Q not only should go to 0, but it has to go to 0 sufficiently fast. It has to go to 0 faster than e to the minus r in order for the corresponding physical perturbations to die out at infinity. So therefore, finding the perturbations means finding bound state of this Schrodinger-like problem with eigenvalue that is strictly less than -1. And so the potential looks rather complicated, but for very large J, when you look at very highly excited momentum mode, angular momentum modes, the potential approaches a universal form for which there are only 2 bound states. It's known for this potential for the Schrodinger-like problem that there are 2 bound states. One is even in R, even in the flip of the wormhole radial direction, and the other is odd. Now, this is only statement true for J bigger than J very, very large that we can make this clean statement. But for general J, you can show this with some help of analytics and some numerics to show that this feature persists, meaning that for each angular momentum modes, there are 2 bound states, one even in an R and one odd in R. And we would like to see what these perturbations do to the action. Okay, so here I've shown you the even and odd bound state eigenfunction for J equal to 0 and J equals to infinity. These are 2 extreme limits. As you can see, the eigenfunctions do not change very much, even if I vary J over a very large range. So basically, the J equals to 2 story would be able to generalize to large value of J. And on the right, I show you the boundary term that I call G. And this is the boundary term for the even perturbations. The even perturbations give you a diverging boundary term at the origin where the wormhole throw is. And so the Euclidean action goes to +infinity, which means that the even bound state modes give a vanishing contributions to the path integral. And so we could discard them. In contrast, the odd bound state eigenfunctions survive as a finite action perturbations. This is because the boundary term is everywhere finite and it actually integrates to 0. So then there's some numerical work you can do to study the spectrum of eigenvalues to see whether the action is increased or decreased. And our conclusion is that the Euclidean action only ever increases by this odd bound state eigenfunctions instead of decreases. And so the axionic wormhole is perturbatively stable. So all the previously found negative modes of an axion wormhole, they are gauge artifact, or as a result of imposing incorrect boundary conditions. Okay, so let me take stock of what we have found. We have analyzed axion gravity and its dual formulation in terms of the 3 form directly with the Lorentzian path integral without going through a Euclidean path integral. And using Picard-Lefschetz theory, we identify which subset of the complex saddle points contributes to path integral computing transition amplitudes. And for the transition amplitude that we compute, as you have seen, there are 4 saddle points. Turns out all 4 saddle points satisfies the allowability criteria of Kontsevich and Siegel, even though only 1 or 2 are selected by the contour deformation. It would be interesting to find out if another principle could single out the saddle points that are selected by the Picard-Lefschetz methods. So so all the saddle points are consistent, but maybe there are secretly other consistency criteria that rule out some of the wormholes, that some of the saddle points that don't contribute to the path integral. We don't know the answer. So one of our main results is that we established the Giddings-Strominger wormhole. The 3-form picture makes gauge invariance and proper boundary conditions transparent. the spectrum of perturbations around the wormhole solutions contains no negative mode. This suggests the interpretation that these wormholes contribute to the non-perturbative energy splitting for degenerate vacua with opposite flux. So you have many degenerate vacuum. So if you flip n by minus n, it still degenerate in energy. The wormhole could contribute to splitting this energy non-perturbatively, rather than interpreting the wormhole solution as mediating decay, as some of the papers suggest. Now, even though our analysis was done for asymptotically flat wormhole solutions, our conclusions may carry over to ADS space as well, because the perturbations, as we found, are localized to the wormhole throat, whose size is much smaller than the ADS radius. So as far as the stability is concerned, our analysis should apply to wormholes in ADS space as well. So at least we rule out one possible interpretation of this wormhole, namely we rule out the possibility that perturbative instability could explain away the puzzle of Euclidean axionic wormholes. We are still left with many possibilities. One of the possibilities is that in string theory, we never see an axion come along. It always comes along with its dilaton partnered. And could the inclusion of the dilaton drastically change the outcome? So in an ongoing work, we study axiodilatonic Euclidean wormhole, and we find that large wormholes tends to fragment into smaller wormholes with the same charge, as the weak gravity conjecture suggests. But we haven't looked at the stability of such systems. It may be that these wormholes are unstable because of the additional dilaton perturbations. Now, another possibility is that there's some obstruction in embedding this wormhole into ADS compactification of string theory. Now, in order for the wormholes to be regular, one can show that there is necessarily a long enough timeline geodesic in the moduli space, as was worked out quite cleanly in this paper at all. Now, the question is, could Swarmland criteria, such as some upgrade version of the distance conjecture, limit the length of the maximum timeline geodesic in field space? That would be another possibility to get rid of the puzzle associated with wormhole and factorization. Now, the wormhole puzzle can also be resolved if the wormhole contribution is canceled by some other contributions, or the wormhole contributions may be reproduced by large corrections to another saddle, as was studied in some of this more controlled two-dimensional gravitational system. I don't know whether this is true for higher gravity. Finally, it may well be that you could find wormholes in higher dimensions that are stable and embeddable into ADS compactification of string theory. In that case, you would have to live with a more general interpretation of ADS CFT, which involves an ensemble average. But in any case, it's clear that further work may teach us whether Euclidean wormholes are in the swampland. So let me stop there. Thank you for your attention.
Does this work involve topology changing, topology change?
Yeah, so we have a section in our paper. So if you take Coleman's story, topology change corresponds to having some alpha parameter. You can see how this affects the path integral. And we do see that the saddle points get changed. The nature and the number of saddle points get changed if you include such contributions.
But in your amplitude calculation path integrals, you had a fixed topology. Is that right? But you're saying that you could handle topology change.
So we have not a direct way, but sort of an indirect way. So Coleman had this alpha parameters way of writing, all these baby universe contributions, and we tested on having some of this non-local time interaction, and and see how this non-local term reflects in the settle point calculation of the path integral. We do see the settle points get correct, that get shifted. So we have one tiny section in the paper that does it, but we don't know what to make out of this sum over higher topologies in general.
Quickly, can you also tell us what you mean by bound states? Because you're talking about perturbative analysis. So where did that come in?
Yeah, bound state means that they are, so it's because I'm solving a Schrodinger-like problem, right? I'm trying to find wave functions that have bounded by this potential. So bound state in the sense of this.
Okay, not in the sense of looking at quadratic perturbative action.
So you have basically massaged the problem,
Yeah.
one-dimensional quantum mechanics problem. As the bound state.
Okay, thank you.
There's one question from online participants.
Oh. Hi.
Who is the person and what's the question?
Person is TAMU, but he somehow left the.
I think he just used the clap hand emoji.
Maybe another question, but for stability analysis, isn't it sufficient to show that the perturbations, they don't grow? Why do we also need the Euclidean action to grow in addition to? Yeah, I mean, isn't it enough? Like, if you find like, is this to be larger than 0? It means that you only get like oscillating perturbations. But you also said you check the Euclidean action also growing with.
Yeah, so here, if I were quick, I would just say that this conclude the stability of the wormhole because the boundary term usually doesn't make a difference.
Okay.
Here we have to be careful, and indeed you see that the boundary term can be negative. Right. So for the odd perturbations, the boundary term is actually negative.
Also, because of the existence of the boundary term,
Yes.
it's not enough to have like this positive mass.
That's right. And I think after we post the paper, the Belgian group previously conclude that the wormholes are unstable. They managed to see the same kind of stability. These are done carefully. And somewhere in the argument, they wanted to argue identical. Right. So I think this group who previously concluded that it was the Giddings-Strominger wormhole was unstable. They revisit the problem with the correct boundary conditions. They saw the same thing, but they wanted to give a quicker argument after they get to this action without solving the spectrum of perturbations. And the tricky part is, as you have seen, right. So they would like to do a different. They would like to argue that this is positive already, without going to this rescale perturbations. They go directly from this,
Okay.
right? And so all these coefficients are positive definite, and you don't have the boundary term if you are dealing with this set of perturbations, right? So it looks like they could conclude it's positive definite much easier. But I think the mechanics of our exercise show that this was a bit too quick, because there are divergent contributions to the path integral. So when the integral is divergent, you cannot do integration by parts so freely. So I think this is a much cleaner conclusion there.
Can you use this technology to deal with membrane amplitudes? I give you a three-dimensional path integral, and it's a nonlinear theory, but maybe you can you use this technology? I wonder. Probably not, right? It's a hard problem.
Yeah, I don't know.
Yeah. Okay. some brave souls do compute membrane amplitudes, by the way.
The audience.
Some Germanic people, Germans do that. Okay, well, thank you.
Thank you.